Okay, so this is the first video for section 9.6. 9.6 will have two videos. This is sort of a strong departure from what we've been doing earlier in chapter 9. So this is called logistic regression, and it is an example of a generalized linear model. So I pause, copy, and then play. Okay, so a generalized linear model, or GLM, of a response variable y as a function of a predictor variable x, it may be appropriate in a couple of scenarios. Okay, so first off, if y is not even close to having a linear relationship with x, linear regression doesn't make a whole lot of sense, but maybe we could generalize it to something that does. Or if our variance of y isn't constant, then a linear model doesn't make sense either, because constant variance is one of the assumptions of the linear regression model, okay? All right, so sometimes though, if one of those two things doesn't work out in our favor for a linear model, we have an option. Sometimes we can find a function of y, let's say h of y, that does allow a linear model in x to approximate it, okay? So that's why it's called a generalized linear model. We're not modeling y, we're modeling a function of y with a linear model, okay? All right, so that's one example of a generalized linear model, and there are many, but the only one we're going to cover in this class is called logistic regression, and it's utilized in a very certain situation or a very certain scenario, okay? So if our response variable y sub I is binary, like 0 or 1, this did happen, this did not happen, okay? If that's the case, then we know the expected value of y sub I is some probability p sub I, for a given x value, a given input. And that probability has to be between 0 and 1. So it could be that I can get the expected value of y. Oh, sorry. If I would hope to model y via a linear function of x, that's crazy talk. Utter and complete ludicrousness, because the expected value of y sub I has got to be between 0 and 1, but a linear model can go way less than 0, can go into the negatives, and it can go way greater than 1. So there's no way a linear model is going to satisfy staying between 0 and 1. So a linear model is crazy talk, okay? The other problem with this scenario is, since y sub I is either 0 or 1, it's Bernoulli. It's a Bernoulli random variable, all right? So it's Bernoulli with some unknown probability p, p sub I, and its variance is given by p sub I 1 minus p sub I, because it's Bernoulli. And that's not constant. Different y sub i's will have different variances, okay? So that's no good. So if I have a response variable that fits this bill, straight up linear regression isn't going to work, but logistic regression, which we'll explore, will, okay? All right, so let's look a bit more at where this could crop up. This type of a response variable could crop up. All right, so why don't you pause the video, copy this down, and then press play. All right, so we're going to use this setup in this example in some of the examples I'm going to illustrate in the second video on section 9.6. So let's say I've got a bunch of accident data, all right? And my predictor variable is going to be x sub I, the age of the driver in an auto accident. So these people have been in an accident. The response variable that I'm trying to predict is y sub I, and that's whether or not alcohol is involved. And let's just assume there are only two scenarios. It's either not involved, y sub I is 0, or alcohol is involved, y sub I is 1, okay? So there, my y sub I is a Bernoulli random variable, okay? All right, so y sub I is Bernoulli, and what we'd like to figure out is a relationship between the x sub I, the age of the driver in the accident, and the probability that alcohol is involved. I can't go after y sub I directly, because like for one 20-year-old, alcohol might have been involved in the accident. For another 20-year-old, alcohol might not have been involved in the accident. But I'm hoping that for both 20-year-olds, the probability that alcohol was involved in the accident can be modeled, okay? All right, so how are we going to set up this logistic regression model? It does take a bit of work. So let's let p sub I denote the probability of an event. It's the probability of one of these y sub i's equaling 1. And then we can define the odds of the event by the probability over 1 minus the probability. So that's the probability of success, air quotes, divided by the probability of failure. right? So for example, let's say the probability of success is 1/3, then the odds would be 1/3 over 1 minus 1/3. So that's 1/3 over 2/3. So that's a half, or I like to think of it as a half over 1. And that tells me the number of successes, I expect half a success per failure, per one failure, okay? So the odds are pretty much telling you how many successes should you expect per failure, okay? Or you could think of this as 1 over 2, so I should expect one success per 2 failures, right? Okay, well, since the probabilities of success are between 0 and 1, you can check, but p over 1 minus p will be between 0 and infinity. This fraction will never be negative because p sub I is never greater than 1. And 1 minus p sub I can get really, really small, close to 0, in which case p sub I is, if that's close to 0, this p sub I is close to 1. So I have 1 over a very small positive. So I'm gonna head towards infinity. Okay. All right. Pause, shift over. All right, so here we're going to actually develop the logistic regression model. So why don't you pause, copy this down. It's a lot of algebra, but algebra is our friend and we love it. And then press play. Okay, so our setup, as a reminder, I've got data x1, y1 up to xn, yn, where each y sub I is either 0 or 1. Y sub i's are Bernoulli random variables, each possibly with their own probability, okay? All right, and we'd like to fit a linear model to the natural log of the odds of success. That's what it turns out we have a shot at getting a linear model for, right? So in other words, I'd like to create a linear model, alpha plus beta xi, for the natural log of the odds, okay? And that's for my data points. All right, so that's the linear regression model, and R is going to help us determine a sensible alpha and beta given our data, right? Let's do some algebra to get a couple of things that are going to be helpful for us in the next few panels. Given this logistic regression model, I can take both sides up as powers of e. So on the left, I just get p over 1 minus p, and on the right, I get e to the alpha plus beta xi. And what I'm now going to do is I'm going to solve for p sub I, right? So first off, I can take my denominator, 1 minus p sub I, and multiply it over to the left. This power, I'm just going to say, is a rectangle, okay? All right, so I get that step. I can run my e to the rectangle through 1 minus p sub I. I can gather the p sub i's over on the right-hand side. So the e to the rectangle p sub I, I'm going to add it to the right-hand side, factor p sub I out of the right-hand side, and divide 1 plus e to the rectangle back over to the left, okay? And I've solved for p sub I, which is right down here, if I replace a rectangle with alpha plus beta xi. Okay. Also, I can take this equation and basically do 1 minus on both sides. So 1 minus both sides. And on the left-hand side, that 1, I can write it with the common denominator of 1 plus e to the rectangle. So 1 becomes 1 plus e to the rectangle divided by itself. So that means on the left-hand side, I can mush these two fractions together via subtracting the numerators. So the e to the rectangles knock each other out, and I'm just left with a 1 over 1 plus e to the rectangle equals 1 minus p sub I. And I got that guy right here, replacing rectangle with alpha plus beta xi, okay? So those two statements are good, handy to have highlighted in your notes. And obviously the linear regression model is central to what we're doing, okay? All right. So we've got our model set up. And here's some evidence why it might be decent. So here's the logistic curve. The expected value of y sub I, since it's Bernoulli, is p sub I. And I've got an expression for p sub I on that last panel. It was e to the alpha plus beta xi divided by 1 plus e to the alpha plus beta xi. There's what its graph looks like, okay? Never goes below 0, never goes above 1. Okay. And what we're going to find is that beta from our logistic regression model, once R gives us an approximation for it, it sort of controls how quickly the log odds ratio is changing. And let's examine that log odds ratio word, okay? So consider two data points we have. I've got x1 and the probability of success associated with x1. And then I can move over a bit, x1 plus delta x, and I'll have a somewhat different probability of success associated with that x value. And what I'm going to do is I'm going to take the odds for P2 and divide it by the odds for P1. And that's called the odds ratio. It's how much is the odds changing, okay? So I can then replace the odds with the e to the alpha plus beta times the x value, right? That's the statement from the previous panel right after the words via algebra. So we replace the odds for P2 and the odds for P1 there. And I can subtract the exponents, and I'm left with e to the beta times delta x, which I summarize there. And if I then take the natural log of both sides of that, I get beta times delta x. And that's called the log odds ratio. So the log of the odds ratio. And so that's showing us how beta is controlling how those odds are changing, right? And that's a good thing to know. So for an example, green doesn't show up too well. Let's say my P1 was equal to a fourth and my P2 was equal to a third. So the probability of success is increasing. Let's just see what happens to the odds ratio. So I'm going to take my P2, the odds, and divide by P1, the odds for P1. So that's 1/3 over 2/3. And 1/4 over 3/4. So let's see, 1/3 over 2/3 is a half. 1/4 over 3/4 is a third. And so that's 3/2, or 1.5, okay? So when my probability of success goes from 0.25 to 0.33, the odds increases by a factor of 50%, okay? And then the natural, and then that 1.5 is going to be modeled, the natural log of that 1.5 is going to be modeled by that beta guy, okay? All right, so last panel for this, and then we'll do some examples in the next video. How do we find the beta and the alpha, okay, for our logistic regression model? Well, we're going to go back to the maximum likelihood estimation. So why don't you copy this out, and then I'm going to talk through it probably slowly. This takes a little bit of believing here. All right, so the likelihood function, I've got all this data, and all this data is basically saying y1 through yn, each of them is either a success or a failure, a 0 or a 1. So what is the likelihood that that happens? Well, I have a p sub I for each y sub I that equals 1. So if y sub I is a 1, that means the probability of success is p sub I. And if the y sub I is equal to 0, this exponent is 1, so that means I get a probability of failure here. So the likelihood of getting the y sub i's as we see them is given by this product over my data points. So if y sub I is a 1, I get a p sub I, this becomes a 0. This becomes a 1. And if y sub I is 0, this becomes a 1 times 1 minus p sub I to the first. So this becomes a 1 minus p sub I. So this function is documenting the probability that y1 is a success, and y2 is a success, y3 is a failure, and y4 is a success, okay? It's documenting all of that, okay? All right. Maximum likelihood estimation process then says, well, let's take the natural log of this likelihood function strictly to make calculus easier. So I'm going to take the natural log of that, which changes the multiplication into addition, and it drags the y sub i's in front of the natural log of the p sub i's, and that product becomes addition, and that exponent gets dragged down in front of the natural log of the 1 minus p sub I, okay? All right, well, then what happens? I've got a y sub I ln of p sub I and a negative y sub I ln of 1 minus p sub I. So I can factor the y sub I out, and that subtraction sign becomes division at p sub I divided by 1 minus p sub I. Right, and then I have the 1 times ln of 1 minus p sub I right there. The natural log of p sub I over 1 minus p sub I, we're hoping that's being modeled by this linear function alpha plus beta xi. and ln of 1 minus p sub I, well, 1 minus p sub I from the first or second or third panel, sorry, 1 minus p sub I can be replaced by this expression. And since this guy is 1 plus e to the power in the denominator, I can flip it to the numerator by dragging a -1 out in front. Okay, that's all to the -1 power. So I get this thing. That's differentiable. So now I'm going to take the partial derivative of this expression with respect to alpha, and you can check through my calculus, but I get that bad boy and set it equal to 0. And I'm going to take the partial derivative of L, little l, with respect to beta, right here, and you can check through my calculus, my first derivative, set it equal to 0. And it turns out that this is ridiculously ugly. It doesn't have what's called a closed form solution. I would not be able to write out alpha equals this and beta equals that. Well, alpha hats and beta hats. There are approximations for alpha and beta. But R can use some numerical analysis techniques to approximate solutions to these two equations. And usually they're using numeric methods. So by the way, if you're finding like, oh, I don't think that stats is for me, numerical analysis, helping computer systems solve, well, approximate complex equations. Oh, there's a fascinating life that'll be richly rewarded for you in numerical analysis if you're interested. Okay, that's the end of this video.